Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to talk on module Energy Harvesting using thin films under the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we are going to see and learn about the different types of energies that can be harvested using thin films. Then one by one, we'll study about the three areas of energy harvesting using thin films. The first area that we are going to cover is the solar energy harvesting using thin films. Solar energy harvesting using thin films. The topic covered here will be using ferroelectric photovoltaic effect. Then secondly, we'll see the magnetic energy harvesting using magnetoelectric effect. Then thirdly, we'll see in detail about the vibration energy harvesting, that is the use of cantilevers. Next, we'll learn about what is a cantilever and why do we require them. And in the end, we'll study in detail about the piezoelectric cantilevers. So before getting into the detail, let's have a brief introduction. As an alternative technology, highly efficient miniaturized energy harvesters using thin film structures can be developed. A lot of researches like working for harvesting energy in different forms like solar energy, vibration energy, magnetic energy, thermal energy, etc. and many more. In the present module, we discuss in detail about the solar energy harvesting using ferroelectric thin films, piezoelectric energy harvesting, and magnetic energy harvesting using piezoelectric thin films. Ferroelectric photovoltaic effect. Researchers have been striving to open different corridors for the production of renewable energy with the evolving demands of the inexhaustible energy and clean fuel sources. With Earth receiving plenty of continual solar energy everywhere from the sun, which is the primary source of the viable clean energy, momentous attempts have been done on gathering light energy through photovoltaic effects, in which light energy is converted into electricity. Photovoltaic effect involves three primary processes. Number one, electron-hole pairs creation under illumination of light. Secondly, breaking away of electrons and holes. And thirdly, the migration of electrons and holes to build the net electric current in a specific direction. The charge dissociation commences ensuing four mechanisms. Number one, granularity. Number two, inbuilt non-centrosymmetry in bulk material. Number three, the heterojunction, such as Schottky barrier, as in conventional silicon-based solar cell. And the number four, built-in electric field originating from polarization. The electric field existing in the space charge region of a p-n junction or heterojunction separates the charge carriers in the conventional silicon-based solar cells. On the other hand, in a ferroelectric thin film, electric polarization gave rise to a net internal electric field throughout its bulk region without being absolutely cancelled by screening charges. Thus, photovoltaic effects are not constrained to any particular region and they can be achieved without creating complexities. Moreover, diffusion do not restricts the charge propagation and output photovoltage is not confined by energy barrier. The exceptional and superior edge of the ferroelectric photovoltaic effect or FPV are: number 1, high output voltage as high as above the band gap. Secondly, polarization controlled photovoltaic response have been intriguing many researchers in this field. Ferroelectric photovoltaic effect has been presented in several perovskite oxides such as bismuth ferrite or BFO, lead zirconium titanate oxide which is the PZT, barium titanate BTO, and the other elemental mechanisms have been mentioned for the same, which includes: number 1 is the internal electric field, which we also called as the depolarization field. Internal electric field effect generated by the polarization. Secondly, metal ferroelectric interface or the Schottky ohmic barrier effect. Then third is the bulk photovoltaic effect or BPVE. At the same time, the photovoltaic efficiency, that is the light to power conversion ability, has been curbed by small current densities. Small current densities of the order of 10 raised to the power minus 9 ampere per meter square, and the large band gaps, typically of the order of 3.5 electron volt of these ferroelectric materials. Therefore, there is a high need of finding an alternative route to tailor the properties of these ferroelectric materials so that the high photovoltages, which can be easily accomplished with modest light intensities, can be obtained and can become a boon for a broad range of applications where low electrical power is recommended. In spite of low conversion efficiency, FPV can be used to empower future solar cells with much new capabilities. The figure 1 showing the schematic diagram depicting separation of charge carriers after illuminating light on bismuth ferrite and barium titanate multilayered photovoltaic cell due to ferroelectric photovoltaic effect. This is an example of a ferroelectric photovoltaic effect in which BFO BTO multilayer is a ferroelectric layer in which the separation of charge carriers occurs due to the internal polarization after the light is impinged through the top electrode as gold. In this structure you can see the substrate is silicon, then the bottom electrode is platinum, then there is a ferroelectric multilayers, and there are gold top electrodes. So the platinum bottom electrode and gold top electrodes are used for the characterization, electrical characterization or connections. And then in the inset we can see that the charges are being separated and moved towards the two electrode, giving rise to the electric field or voltage. Now let us discuss why vibration and magnetic energy harvesting is more preferred over solar energy harvesting. Major challenge of the 21st century is to develop self-powered systems especially those which can be operated using energy harvester as well as electrical power sources. Self-powered devices are used in a wide range of wireless applications ranging from encapsulated implants to industrial process monitoring. Furthermore, the increasing demands of mobile devices such as wireless sensor networks and the recent advent of extremely low power electrical and mechanical devices make such energy harvester sources very attractive. Traditional power sources such as batteries have various limitations in current wireless remote sensor systems, which include their large volume, limited lifetime, environmental pollution, and huge maintenance requirements, etc. Exploring the possibilities of renewable, sustainable, and green energy sources to replace fossil fuels is one of the most significant and challenging issues in the energy research. A number of ambient sources such as sunlight, heat, magnetic energy, and mechanical vibrations have been studied for harvesting to generate useful electrical voltages. Among them, mechanical vibrations and magnetic energy are independent of weather conditions and offer great potential in application as energy harvesters. Numerous materials have been investigated in the literature which can convert the natural form of energy, particularly magnetic and mechanical vibrations, into the useful voltage. The current surge of activities in magnetoelectric field has led to a way for the development of new generation harvesting devices. Performance of these energy harvesting devices strongly depend on the magnetoelectric systems being used, and various combinations of ferroelectric and ferromagnetic materials are utilized. Several reports are available regarding energy harvesting using bulk ceramics from mechanical vibrations, but only few reports are available on the generation of power from the thin film based energy harvesting systems. Thin film based systems offer several advantages over the bulk systems, including flexibility of tailoring the material properties, miniaturization, etc. In order to develop a dual energy harvester, that is, obtaining voltage from electromagnetic energy as well as mechanical energy, it is important to fabricate a cantilever based magnetoelectric structure which could generate electrical power also in correspondence to mechanical vibrations in the cantilever. Now let us learn about the magnetoelectric effect or ME effect. Layered multiphoric materials are candidates for the next generation multifunctional devices. In these structures, the interaction between ferroelectric and the ferromagnetic layers produce new coupled magnetoelectric or ME effect. The ME effect is defined as an induced electric polarization represented by capital P of a material with an applied magnetic field represented by capital H or vice versa. The magnetoelectric effect can be direct magnetoelectric effect and converse magnetoelectric effect. The ME effect comes from the local exchange between internal orderly magnetic structure and ferroelectric sublattice. Unfortunately, single-phase materials exhibit weak magnetoelectric effect, which explains their limited applications. Magnetoelectric effect in layered structures provide an alternative or exhibiting higher ME effect due to mechanical coupling between the piezoelectric and ferromagnetic layers. The figure shown here shows the mechanism in a direct magnetoelectric effect in which you can see the coupling between the magnetic layer and piezoelectric layer, in which the magnetic field, that is the H, converted to S, which is strain, then it is to T tension, then D, and then finally into the electric field E. The principle of magnetoelectric effect in the composite system is that the magnetic field induced strain in the magnetostrictive component is transferred to piezoelectric component through elastic coupling, resulting in a piezo-induced voltage and vice versa. It means that in the piezoelectric or piezoelectric composites, in the presence of an applied magnetic field, piezomagnetic particles change their shape due to magnetostriction effect, and this strain is passed to the piezoelectric phase, resulting in an electric polarization change, which is shown in figure 2. Thus, the magnetoelectricity in the composite system is a product property and needs biphasic surrounding to exhibit the complex behavior. The primary magnetoelectric composite materials become magnetized when placed in an electric field and electrically when placed in a magnetic field. The term magnetoelectric coefficient is the voltage generated in the piezoelectric due to the applied magnetic field per piezoelectric thickness, and it has the units of volts per centimeter or oersted. That means volts per centimeter oersted. The magnetoelectric device can be operated in 4 configurations, which are as follows. The first configuration is LL mode or longitudinal mode. In this mode, magnetic field and electric field are along the surface. The second mode is the LT mode or the longitudinal transverse mode. In this mode, magnetic field is along the surface and electric field is perpendicular to the surface. The third mode is TL mode or the transverse longitudinal mode. In this mode, magnetic field is perpendicular and electric field is along the surface of the system. The fourth and the last mode is TT mode or the transverse mode. In this mode, magnetic field and electric field are perpendicular to the surface. One of the advantages of magnetoelectric devices is that it can be used as energy harvesting device, as the input source of energy which can be taken from the nature. Now let us discuss why cantilevers. Cantilever based detection principle is the heart of scanning instruments such as atomic force microscopy, which we commonly call AFM, and other magnetic force instruments. Piezoelectric bimorph cantilevers were used in 1991 for scanning force microscopy for the detection of the surface force between sample surface and the tip of the cantilever. However, unwanted incubated vibrations in the cantilever limited the sensitivity of AFM. Then Cunningham et al. In 1995 devised an efficient way to resolve this problem by using an active piezoelectric element and optical vibrational sensing. It was suggested that the use of films instead of bulk ceramics can provide improved vibrational control and actuations along with better sensitivity. With the development in thin film deposition techniques, piezoelectric materials such as zinc oxide, that is ZNO, and lead zirconium titanate, that is PZT, have emerged as ideal candidates for this purpose. Other than the sensing applications, piezoelectric cantilevers also serve as intermediaries for transferring mechanical energy. The mechanical energy due to cantilever motion can be converted into electrical energy via piezoelectric effect. Now let us discuss about the piezoelectric cantilevers. The vast majority of piezoelectric energy harvesting devices uses a cantilever beam structure. A cantilever beam, by definition, is a beam with a support only at one end and is often referred to as fixed free beam. When the generator is subjected to vibrations in the vertical directions, the support structure will move up and down in sync with the external acceleration. The vibration of the beam is induced by its own inertia. Since the beam is not perfectly rigid, it tends to deflect when the base support is moving up and down. You can see this phenomena of deflection in the figure given below. Typically, a proof mass is added to the free end of the beam to increase the deflection amount. This lowers the resonant frequency of the beam and increases the deflection of the beam as it vibrates. The larger deflection leads to more stress, strain, and consequently a higher output voltage and power. Hence, by adding the variable proof mass, the resonance frequency of the cantilever can be tuned. The cantilevers can be classified into two categories: unimorph, number 1, and second category is bimorph. When the beam has only a piezoelectric layer attached to a substrate layer, the device is known as unimorph. When a substrate material is sandwiched between two piezoelectric materials, the device is known as a bimorph. The operation of cantilever benders is relatively simple. If one layer is in compression, the other layer is in tension. The stress in one layer affects the stress in the other layer. For example, in a piezoelectric unimorph, when an electric field is applied to the piezoelectric layer, the piezoelectric layer expands or contracts, where as the non-piezoelectric material is not affected by the electric field. This causes the cantilever to bend. The opposite also occurs when the beam undergoes bending from an applied force from an external vibration source. This bending causes a charge to be generated between the electrodes of the piezoelectric layer. In this situation, energy can be easily harvested from the electrodes. The given figure 3 here shows the mechanical vibrations in piezo cantilever due to the piezoelectric effect. So you can see the demonstration of strain in the cantilever, where the mass is there at the one end and the mass is given the vertical displacement. Then due to this, there is production of a voltage. Now let us discuss the cantilever in detail. A structural element anchored at one end to a support and subjected to load transfer to its axis at the other end is known as a cantilever. A cantilever is classified under category of beam. In general, a beam can be either free from any axial force or the effect of this force may be negligible. Usually, a beam is considered in horizontal direction and load in vertical direction. The load can be of two types. Number one, concentrated load, and number two, distributed load. The concentrated load is assumed to act at a particular point, though in practice it may be distributed over a small area. On the other hand, distributed load is one which is spread over the length of the cantilever. However, the rate of loading may be uniform or may vary from one point to another. There are different types of supports for beam, which are as follows. The first one is roller support. In case of roller support, a beam rests on a sliding surface like a roller or a flat surface. This you can see in the given figure 4 below, which shows the schematic of roller support. The roller support can sustain a force normal to its surface, as the possible movement on the supporting surface does not allow any resistance in that direction. Therefore, the reaction capital R along the rolling surface is zero and it is present only normal to the surface. So you can see the schematic of roller support given below in the figure 4. The second type of support is the hinged support. In case of hinged support, the possibility of translation, displacement of the beam is zero. However, rotation is possible. In this case, there can be reactions in vertical as well as horizontal direction. In the figure given below, you can see the schematic of the hinge support, in which both vertical, that is capital R, and horizontal, that is capital H, reactions are possibly seen because the translation displacement is zero, but the rotation is allowed. The third type is the fixed or encaster or built-in support. A built-in to a rigid support which does not allow any type of movement or rotation is known as fixed or encaster or built-in support. A fixed support exerts a fixed moment and a reaction on the beam. This can be illustrated well from the figure 6 given below, which shows the schematic of built-in support. A beam with one end fixed and the other end free is called cantilever. There is vertical reaction and moment at the fixed end, represented by capital R and capital M, and is called the fixed moment. In the present case, cantilever beam is made which is supported from one end, that is the fixed support, and free from other ends. In this case, cantilever beam transfers the load to the rigid support where it manages the moment of force and shear stress. In the given figure 6, you can see the schematic of built-in support. So let us discuss about the shear force. What is a shear force? Shear force is one of the most important parameters in case of cantilever. It is an unbalanced vertical force on one side, that is other than the fixed support of the cantilever beam, and is the sum of all the normal forces. In other words, it represents the tendency of either portion of the cantilever to slide or shear laterally relative to the other. Shear force is considered positive when the resultant of the forces to the left of a section is upwards or to the right downwards. Now the next terminology is bending moment. Bending moment is another parameter of interest while understanding the theory behind cantilever. Bending moment at some section of the beam is defined as the algebraic sum of the moments about the section of all forces on one side of the section. So students, let us now summarize what we have learned in this module. First of all, we learned about the different types of energies that can be harvested using thin films. Then we chose three major areas in the present module in which the energies are harvested using thin films. The first area is the solar energy harvesting using thin films by ferroelectric photovoltaic effect. Second area that we studied is the magnetic energy harvesting using magnetoelectric effect. The third one is the vibration energy harvesting using cantilevers. Then in the end, we studied the piezoelectric cantilevers in detail. Thank you.